We're going to discuss the vertical construction of PCBs, which has a serious effect on the performance of RF signals. The term stack-up refers to the design of the vertical dimension of a PCB. How far apart layers are from one another, what materials they're made of, and what types of signals are predominantly routed on each layer. This has a bunch of possible consequences. First, the order of layers matters a lot for ensuring that signals don't radiate or interfere with one another. The safest way to route a board is to ensure that high-frequency signals are adjacent to ground planes, as shown in this figure, which has a bunch of benefits that we'll discuss on the next slide. Other layer tricks include placing power planes adjacent to ground planes for enhanced decoupling capacitance, and putting low-frequency control signals on non-critical layers. Second, the substrate material in a PCB stackup affects performance. The substrate determines the permittivity of the PCB, and it also has a loss tangent that determines the high-frequency attenuation of transmission lines that are built on the PCB. Most PCBs are made out of a fiberglass material called FR4, and a thick piece of FR4 called the core provides the structural support for the PCB. Copper sheets are then laminated onto the FR4 and etched to create wires, and thinner layers of FR4 are applied outside of the copper layers to repeat the process if more layers are desired. These outer layers are often referred to as cladding. However, you're not required to use FR4, and you can also use other ceramic substrates like Rogers that have much lower loss tangents. Unfortunately, these ceramic substrates are more fragile, often toxic, and accordingly much more expensive to use in manufacturing. That means there's a huge incentive to make boards out of FR4 if you can, but FR4 has a speed limit of about 10 GHz due to attenuation. Even reaching 10 GHz is challenging, and it depends on the type of FR4 and the talents of the fabrication house. Similarly, Rogers from low-quality fabricators might underperform FR4 from high-quality fabricators, so make sure you know your vendor well when you're ordering a PCB. Third, the separation between planes has a dramatic effect on the capacitance between layers and the inductance of traces. This means that designing transmission lines depends on the separation between layers and even the thickness of the copper. You'll need to study these properties closely. It's worth expounding further on the virtues of ground planes. We can see one in action by looking at the renderings of the fields underneath the trace that's running vertically in the figure on the left. Electric field is purely vertical between the trace and the ground plane under the trace, but fringing fields cause the signal in the line to spread out a bit to the left and the right. Bringing the ground plane closer will reduce the spread of the electric field. Similarly, B-field loops around the current in the outgoing trace, but the current in the return path spreads out on the ground plane below the trace, which causes a wider magnetic field loop as well. Moving the trace closer pulls the return current distribution in closer, and accordingly keeps the magnetic field more tightly coupled. On the right, I've drawn a substitute for ground planes that's sometimes used, called a ground pore. Ground pores are large sheets of metal on the same layer as a trace that are connected to ground. They don't work as well as ground planes because fields need to couple to the left and the right, and there's a much smaller surface area to do so. I wouldn't recommend relying on them without an underlying ground plane, except in extreme circumstances like two-layer boards. If you do have an underlying ground plane, then you might want to pay attention to the blue dots I've drawn on this. Those blue dots are supposed to indicate vias, and this pattern of vias is called a via fence. It's used to connect a ground pore to an underlying ground plane with very low impedance, because all of these vias are in parallel and they're widely distributed throughout the trace. Most of the RF designers I've met are very positive about via fences, arguing that they help with signal shielding. But I don't think that's entirely correct. Via fences do a really good job of connecting the ground pore to the ground plane, which is useful in and of itself because you don't want big floating pieces of metal around. But they're not going to electrically interact with the transmission line trace unless the ground pore is very close to the trace. And if you do make the ground pore very close to the trace, then you're making a different kind of transmission line. When you make that spacing very narrow, you're designing something called a coplanar waveguide, and in that case the VFNs can be quite important. However, if the spacing between the trace and the pore is 5h or greater, where h is the height of the FR4 or the substrate between your trace and your ground plane, then the pores aren't going to interact super closely with the trace. It's also worth noting that I included this equation down here to show about how the return current spreads out, and it depends on the dimensions h and d, where d is a distance from the center of your trace and h is, again, the separation between your trace and the ground plane. So in summary, Stackups specify materials, thicknesses, and purposes of layers in PCB. Stackups have a strong influence on radio frequency performance. Substrates can limit high frequency behavior because of the loss tangent, and FR4, the most popular substrate, maxes out around 10 GHz. And you should make sure ground planes are near fast signals. They help confine fields.